Welcome to the Deep Dive. Today we're going deep into the world of electrocatalysis.
Oh, yeah.
And this is a field that's sparking a lot of excitement, especially when it comes to generating clean energy.
Mm-hmm.
We're talking green hydrogen production through water electrolysis,
Right.
turning simple water into a powerful fuel source.
Yeah.
And, our listener wants to know more about how it works at a deeper level.
Okay.
And luckily, we've got a stack of lecture notes
Okay.
and some cutting-edge research to break it all down.
Excellent.
So,
Yeah, it's a really exciting area.
yeah,
Electrocatalysis sits at the crossroads of chemistry and electricity.
I like that crossroads.
Yeah.
Chemistry and electricity.
Giving us the tools to create and store energy in a way that's sustainable.
Okay, so these notes start with catalysts.
Okay.
We hear that term thrown around a lot, but what's the real deal with catalysts?
Think of catalysts as facilitators.
Okay.
They speed up chemical reactions without getting used up in the process. It's like they're choreographing a dance, making sure everything moves smoothly and efficiently.
So they're like the enzymes of the chemical world.
That's a great analogy.
Right, helping things happen faster.
Just like enzymes in our bodies, catalysts make reactions happen more efficiently.
Okay.
Now, there are different types of catalysts.
Okay.
Some are transition metal complexes, others work with light.
Okay.
Those are photocatalysts, but the ones we're focusing on today are electrocatalysts,
Right.
and they're key for water electrolysis.
Right, because to split water into hydrogen and oxygen, we need electricity.
Yes.
That's where electrocatalysts come in, helping those reactions happen with less energy waste.
Exactly. Electrocatalysts use electricity to drive the reactions, making them essential for producing hydrogen fuel.
Okay.
The specific reaction that creates the hydrogen is called the hydrogen evolution reaction.
The notes mention that a lot.
Yeah.
The hydrogen evolution reaction, or HERR for short,
Right.
seems like that's where the magic happens.
It is. And to really understand how it works, we need to take a quick detour into electrochemistry.
So like a mini crash course on the language of electrons.
Yeah.
Lead the way.
Think of electrochemistry as the study of how electrons move between substances.
Okay.
This movement is called oxidation and reduction, or redox for short.
Redox, okay.
Basically, one substance loses electrons, that's oxidation, and another gains them, reduction.
Okay, so kind of like passing a ball back and forth, but with electrons.
Exactly.
Got it.
And the place where this exchange happens is important.
Okay.
Reduction occurs at the cathode, while oxidation happens at the anode.
Oh.
Think red cat.
Okay.
Reduction at the cathode.
Red cat. I'll remember that.
Yeah.
Simple and catchy.
Good.
So we've got these electrons being passed around. Are all substances equally eager to play this game?
Not at all.
Okay.
Some substances are electron hoarders, while others are happy to give them away.
Okay.
Scientists have ranked substances based on their electron affinity. That's the electrochemical series. Okay. The ones at the top, like fluorine, are like electron magnets, strong oxidizers.
Okay.
And those at the bottom, like lithium, are electron donors,
Okay.
strong reducers.
So it's like a popularity contest for electrons,
I like that.
right? Some are more popular, others are left hanging out.
Now, to harness this electron flow for something useful, we need electrochemical cells. These are like tiny arenas where the redox reactions take place.
So like a battle of the elements, and the prize is those electrons.
You got inside these cells, we have electrodes, which conduct electrons, and electrolytes, which conduct ions.
Okay.
The action happens right at the surface of the electrodes, and the ions in the electrolyte keep everything balanced, making sure the circuit is complete.
It's amazing to think about these reactions happening at that tiny interface between the electrode and the electrolyte.
It is. Now, remember how we talked about electron affinity?
Yes.
Well, electrons naturally want to move from a higher energy state to a lower one. It's like a ball rolling down a hill. It's all about potential energy.
Okay.
The electrode is designed to create conditions that make this electron transfer favorable.
So the electrode is kind of like shaping the landscape, creating a slope for the electrons to follow.
Precisely. The steeper the slope, the faster the electrons flow and the faster the reaction goes. Now, this brings us to electrocatalysis itself.
Okay.
Remember, these reactions are happening at the surface of the electrode.
Right.
The material that the electrode is made of plays a big role in how efficiently the reaction happens.
Right.
That's where the electrocatalyst comes in.
So it's not just about having the electrons flow, but also about providing the right stage for the reactions to take place.
Exactly. The right electrocatalyst acts as the ideal platform for those electron exchanges to occur, like setting up the perfect dance floor. But we also need to consider how things move towards that dance floor that's mass transfer.
Make sure all the dancers get there on time.
Exactly. Now, there's a key concept here called the Sabatier principle. It states that the interaction between the catalyst and the reactants can't be too strong or too weak. It needs to be just right.
Okay.
Imagine trying to stick magnets together too close. They repel too far. They don't attract.
Yeah.
There's a sweet spot where they connect perfectly.
It's like the Goldilocks principle of catalyst design.
Exactly.
Like the binding needs to be just right.
And when scientists evaluate electrocatalysts, they look at a few key things.
Okay.
Activity, stability, and selectivity.
Okay.
Activity is all about how fast the reaction happens. Stability refers to how long the catalyst lasts.
Okay.
And selectivity ensures we're getting the desired products.
So we want a catalyst that's fast, durable, and picky about what it produces.
You got it.
Seems like finding that perfect catalyst is pretty important for making green hydrogen production efficient.
You've hit the nail on the head.
Right.
Our goal is efficient, sustainable hydrogen production.
Okay.
And to get there, we need catalysts that are optimized in all those aspects.
Okay, so we've covered the basics of catalysts, taken a quick dive into electrochemistry.
Right.
Learned how important the electrode surface is. I'm ready to hear more about how this all comes together to actually split water.
Perfect. Let's jump into the specifics of electrochemical water splitting.
Let's do it.
So water splitting, it's exactly what it sounds like. We're using electricity to break those water molecules apart into their basic building blocks, hydrogen and oxygen.
So instead of burning hydrogen to make energy, we're using energy to make hydrogen from water.
Right.
That's pretty cool. But how do we actually break those water molecules apart?
Imagine a container of water with 2 electrodes dipped in Cu. We apply electricity, and at the cathode,
Okay.
the negatively charged electrode water molecules gain electrons. This splits them into hydrogen gas and negatively charged hydroxide ions.
Okay.
Meanwhile, at the positively charged anode, those hydroxide ions lose electrons and combine to form oxygen gas and water.
So we're basically using electricity to rearrange the atoms in water, pulling out the hydrogen and leaving the oxygen behind.
Exactly. It's like a carefully choreographed molecular dance, and the electrocatalysts are there to make sure everyone hits their marks. Now, each half of this reaction, the hydrogen evolution reaction at the cathode and the oxygen evolution reaction at the anode, has a standard potential that tells us how easy or difficult each step is.
So is one side of the reaction like making the hydrogen easier than the other?
It often is for the hydrogen evolution reaction, or HIR. It's actually energetically favorable. It's got a negative standard potential, about -0.83 volts. But for the oxygen evolution reaction, the OER, it's positive about plus 0.40 volts. This means we need to put in energy to make it happen.
I see. So we need to push the oxygen evolution reaction uphill a bit, energetically speaking.
You got it, to get the overall cell potential, the energy needed to drive the whole water splitting process.
Yeah.
We add those 2 half-reaction potentials together. That gives us about 1.23 volts.
So that's the minimum energy we need to put in just to break even, just to split the water.
Right.
But you mentioned that those catalysts are there to improve efficiency. How does that work?
Remember, catalysts are all about lowering the energy barrier for reactions in water splitting. We call the extra energy needed beyond that theoretical minimum the overpotential. A good catalyst reduces this overpotential, making the process more efficient.
So a better catalyst means less energy wasted and more hydrogen produced. It sounds like finding those great catalysts is crucial.
Absolutely, and researchers are working hard to find the best catalyst for each half reaction. For the HR, platinum is a star performer.
Platinum, I know that's used in jewelry. It must be expensive.
It is, which is why researchers are looking for cheaper alternatives for large-scale hydrogen production. One promising material is molybdenum sulfide. It's showing real potential as a cost-effective replacement for platinum in the HR.
So molybdenum sulfide is like the up-and-coming star ready to take over from the platinum superstar.
You could say that now for the oxygen evolution reaction, or OER, things get a bit trickier. It's often the bottleneck in water splitting because it involves a more complex 4-electron transfer process.
So splitting water to make oxygen is the harder part, the one we need to focus on improving.
It often is, and for this reaction, certain oxide and hydroxide-based materials are showing promise-layered double hydroxides, or LDHs containing nickel, cobalt, or iron, are particularly interesting. They have good conductivity and are effective at catalyzing the OER.
It's fascinating that each side of the reaction needs its own special type of catalyst, like having different tools for different jobs.
That's a great analogy. Now, another interesting thing about the OER is that the catalyst can actually change during operation. It's called the pre-catalytic effect. The catalyst evolves as it works.
It's like it's learning on the job.
Exactly. But there's another layer of complexity here. The environment in which these reactions take place plays a role too. It matters whether it's acidic or alkaline.
So the water we're splitting, should it be more like lemon juice or more like soapy water? Does that make a difference?
It makes a huge difference. The pH of the water affects the reaction mechanisms and the types of catalysts that work best.
I see. So we need to tailor the whole system, the catalysts, the conditions to work together smoothly.
Precisely in acidic conditions, catalysts based on platinum, ruthenium, or iridium are often favored. These metals can handle the harsh acidic environment.
They sound like tough metals, but I'm guessing those come with a high price tag as well.
You're right. Cost is a big factor in alkaline conditions. We can often use catalysts based on nickel, iron, or cobalt. They're more stable, less expensive, and the systems tend to last longer.
So alkaline conditions are more budget-friendly.
They can be. Acidic conditions can operate at higher current densities, which means you produce hydrogen faster, but they require those expensive catalysts. It's a classic trade-off.
So it's like choosing between a high-performance sports car and a reliable work truck. Each has its own advantages and disadvantages.
That's a great way to put it. Another difference is the membrane used in the electrolyzer, which is the device where the water splitting happens in acidic environments. Proton exchange membranes, or PMs, are used in alkaline environments. It's anion exchange membranes, or AEMs.
So it's a whole system with all the parts working together, the catalyst, the pH, even the membrane, and there are even more factors at play, right?
Absolutely. We've only just scratched the surface. There's a lot of work being done to optimize the catalyst's structure, how it's applied to the electrode, and how to manage those gas bubbles that form during the reaction.
So it's not just about the material itself, but how it's shaped, arranged, and how we manage the environment around it.
You got it. Catalyst performance is a combination of intrinsic properties, those inherent to the material, and extrinsic properties, which are external factors that we can control.
So like a musician, their talent is intrinsic, but their training and the quality of their instrument are extrinsic factors that also impact their performance.
Exactly. Think about the shape of the catalyst particles, how densely they're packed on the electrode, even how rough the surface is. All these things impact how well the catalyst interacts with the water molecules and helps the reactions along.
Okay, so it's like fine-tuning a musical instrument to get the best sound, but there's also the issue of bubbles you mentioned.
Right, as hydrogen and oxygen are produced, they form bubbles on the electrode surface. If those bubbles stick around, they block access to the catalyst and slow down the reaction.
So it's like we need to keep the dance floor clear so everyone can keep moving.
Perfect analogy. Managing those bubbles, especially when we're trying to produce hydrogen quickly at high current densities, is really important now to give you a real-world example of how researchers are designing these catalysts. Let's take a closer look at a specific OER catalyst, a mixed metal oxide called IRUOX.
Okay, what's special about that one? So we're talking about this IRUOX catalyst.
Right.
What makes it so special for the oxygen evolution reaction?
Well, it's a clever combination of iridium, ruthenium, and tungsten.
Okay.
Iridium and ruthenium are known for their high activity in acidic environments, but as we've discussed, they're expensive.
So adding tungsten is a way to make the catalyst more affordable.
Exactly. Tungsten helps bring the cost down and also enhances the catalyst's activity.
So it's like finding a teammate who's both talented and budget-friendly. How do they actually make this catalyst?
They use a special polymer called polyethylenamine, or PEI, during the synthesis.
PEI.
It acts like a metal magnet, attracting and binding the metal ions together.
So PEI helps to assemble the catalyst like a scaffold.
Precisely. Once they've created this IRUOX catalyst, they need to study it carefully. Scientists use a whole array of techniques to understand its structure and properties.
It's like giving the catalyst a thorough medical checkup, right?
That's a great way to think about it.
Making sure everything is in order.
They use high-resolution microscopes to visualize the catalyst's structure, almost like taking a photograph at the atomic level. This is called high-resolution transmission electron microscopy, or HRTEM-E. Then they use techniques like energy dispersive X-ray spectroscopy, EDS, to figure out which elements are present and in what proportions. And to understand how the atoms are bonded together, they use a technique called X-ray photoelectron spectroscopy, or XPS.
Wow, it's amazing how much detail they can get about these tiny structures. So what did they find out about IRUOX after all these tests?
They found that the tungsten plays a crucial role. It influences the chemical states of iridium and ruthenium, which boosts the catalyst's activity. They also compared it to a catalyst made of just iridium oxide and found that the IRUOX outperformed the simpler catalyst.
So it's a case of teamwork, making the dream work, combining those different metals makes a more efficient catalyst. But once you have a promising catalyst, how do you actually know how well it performs in a real water splitting setup?
Great question. There are a bunch of electrochemical methods scientists use to evaluate how well an electrocatalyst works. One common technique is called linear sweep voltammetry, or LSV. It's like taking the catalyst for a test drive.
Okay.
They gradually increase the voltage and measure the current that flows, essentially seeing how much effort it takes to get the reaction
So
going.
it tells you how easily the catalyst can split water at different voltages.
Exactly. Another method is Tafel analysis. This gives us insight into the reaction kinetics, how fast the reaction happens at different potentials.
So it's a way to measure the catalyst's speed and efficiency.
Exactly. And then there's electrochemical impedance spectroscopy, or EIS, which helps identify any bottlenecks in the electron transfer process. It's like checking for any roadblocks on the electron highway.
So making sure everything is flowing smoothly. Are there any tests to see how long these catalysts last?
Absolutely. Chronopotentiometry is used for stability tests. They apply a constant current and see how the voltage changes over time. It's like a stress test to see how well the catalyst holds up under pressure.
This has been an incredible journey into the world of electrocatalysis. We've gone from the basic idea of catalysts to the intricate dance of electrons and the challenges of splitting water efficiently.
It's been a pleasure diving into this topic. The research in this area is moving so fast, and it's exciting to see how electrocatalysis is paving the way for a cleaner, more sustainable future.
We started with your question, how can we use water to create clean energy? Well, water electrolysis powered by renewable energy is a really promising answer, and at the heart of it all are these amazing electrocatalysts.
Absolutely. As we move towards a hydrogen economy, finding efficient, durable, and cost-effective catalysts is going to be key. There's still so much to explore and discover in this field.
So to all our listeners out there, keep learning, keep exploring, and keep asking those big questions about how we can create a better future with science. Thanks for joining us for another deep dive.